Hello students, in this today's lecture we are going to learn about operational amplifier as a subtractor. Till now I have covered all the concept in the operational amplifier which are there in our syllabus. Now this is the last concept of this particular chapter. Let me begin with the concept. Here in this concept, what we are studying exactly? Operational amplifier as a subtractor circuit. It is also called difference amplifier. What is subtractor? Subtractor is a circuit which tells the difference between the two values. As like we used to do subtraction, where two numbers, if it is there, we subtract from one another. Whatever resultant value we are going to get, that is the subtractor result. Same thing we are going to do with the help of operational amplifier. Let's begin with the explanation. This is the circuit diagram of operational amplifier which act as a subtractor circuit. Analyze this circuit diagram. The part of the output is fed back to the input, that is to the negative terminal, hence negative feedback is used. Two resistors are connected in both the terminals, negative terminal as well as positive terminal, and named as RF and RF, R1 and R1. That indicates that the resistance values of these both the resistors are same. The resistance values of these both the resistors are same. And two independent voltages are applied here to the operational amplifier. Now output what you are going to get is V0, that is equal to RF divided by R1 into bracket V1 minus V2. With this voltage is subtracted from this V2, so that is what the resultant value you are going to get. Now this is our objective, RF by R1 into V1 minus V2. This V1 minus V2 is nothing but subtraction. RF by R1 should be 1 to get the subtraction. So choose RF and R1 in such a way that these values should be same. That means you should get 1. Now how to arrive at this expression? That is based on the derivation. Let's try to understand the derivation to achieve this expression. So we have already told about the circuit construction. Now let's use the superposition theorem for this derivation. What superposition theorem tells? Whenever you are using two independent voltage sources or current sources, one voltage source or one current source to be acting and other voltage or current source should be grounded, or it should be, if it is a voltage source we have to short it, if it is current source then we have to make a open circuit, and we should do the derivation. After deriving these with respect to keeping one constant, that means one's acting and another one is grounded, the resultant of both these voltage expressions to be added together to get the total value. So let's see how we will do it. Now the explanation is whatever written is same as what I have explained right now. Now let's see. Consider V1 and V2 both are independent voltage source, and now using superposition theorem it says that when one source is acting, other source will not act, or it has to be ground, or it has to be short. If it is voltage source you have to short, if it is a current source we have to make open circuit. Now consider first case, V2 is not acting and V1 is acting. That is what V2 So here I have considered V2 is acting and V1 is ground. Here small mistake is there, please correct it. This I have shown in the first diagram as V2 and this one I have considered as a V1, but in this diagram I have denoted with V1, but you need to change it to V2. Please change it to V2 and this V1 is ground. That means V2 is acting and this we are making it is ground. Then when you ground it, now look at this. Here one node is there. Where three wires are connecting together, it forms a node. Where three wires are connecting, it forms a node. And where node is formed, their voltage generated. And we need to determine the voltage at that node. Now determine the voltage at this node and I have denoted with VA. To determine this VA, we need to use voltage divider rule. What is that voltage divider rule? VA is equal to RF divided by RF plus R1 into this voltage, and the voltage at this side is 0. So put that value. So now use voltage divider rule at node A. VA is equal to RF divided by RF plus R1 into 0. This 0 is this voltage. So when you multiply this 0 with this equation, then simply VA becomes 0. When VA becomes 0, then again if you draw the circuit, that time this V2 is acting, same thing we have drawn, but at the positive terminal this VA you are showing directly with the ground. That means VA is at 0. As we have studied virtual ground concept, whatever voltage at the positive terminal, the same voltage will appear at the VB also. That means at the negative terminal also, because of virtual ground. That is what I have written here. VA is 0 potential, hence VB is equal to 0 due to virtual ground. Hence I can write, you can use KCL equation at this node to determine the value V2 minus VB divided by R1. At KCL, this current is I1, this current is IF, and this current is I, and I is equal to 0 because of infinite impedance. These all things you have know, so I have not written there. So I1 is equal to IF. I1 is what? V2 minus VB divided by R1. Same thing I have represented here. That is equal to IF is what? VB minus V0 divided by RF. So same thing I have expressed here. As you know, VB is 0, substitute the value, that becomes V2 minus 0 divided by R1, that is equal to 0 minus V0 divided by RF. Now the expression becomes this V2 you take this side and this RF and negative take this side. Then what happens? V0 divided by V2 is equal to minus RF by R1. Take this V2 also this side, then it becomes output voltage equation V0 is equal to minus RF divided by R1 into V2. So when V2 is acting, so this is the output voltage what we are going to get. Now next, keep this V2 short circuited and consider V1 is acting. So in the next case, what we are going to see, now V1 is acting and V2 is ground. So here I have made this ground and V1 we are using it. Again I need to determine this voltage at this node using divider formula, voltage divider formula. VA is equal to RF divided by R1 plus RF into V1. So VA is equal to this expression I am going to get. After getting this expression, I will change this diagram to this. I will keep this same thing as it is, but instead of this registers and all those things, directly I will write VA because I know this VA value. I know this VA value. Hence directly I will write VA only. Above circuit is a non-inverting circuit. Look at the things here, because At the positive terminal you are supplying a source voltage, and this negative terminal you have grounded. As you have studied non-inverting operational amplifier, this circuit looks like, or it operates as a non-inverting operational amplifier only. Hence the gain of this non-inverting operational amplifier is already we have determined in lecture 4. Please go through that lecture 4. AV is equal to 1 plus RF by R1. Now what is AV? It is a voltage gain. Voltage gain is nothing but output voltage divided by input voltage. That is what I have written here. Then next thing, multiply this into V input. So V naught is equal to 1 plus RF by R1 into V input. But here I will not write V input as a V in, because here input voltage is VA and that voltage we have already determined. So I will write VA. So here VA value I will substitute, because already it is determined VA, that is RF divided by RF plus R1 into V1. So I will substitute, instead of VA I will write RF divided by RF plus R1 into V1. Now cross multiply this. So R1 plus RF divided by R1 into RF divided by RF plus R1. So this RF plus R1 and this RF plus R1 get cancelled. What remains? V naught is equal to RF divided by R1 into V1. This is the output voltage expression when V1 is acting, and this is the voltage equation when V2 is acting. Now as per superposition, to get the resultant voltage, what we need to do? We have to add this as well as this expression. So you are going to get V naught is equal to V naught at inverting plus V naught at non-inverting. So minus RF by R1 into V2, I have same expression I have substituted, plus V naught at non-inverting is nothing but RF plus RF by R1 into V1. Now this RF by R1 and RF by R1 is common, take it common, then this minus sign is there, that I will take inside. So it becomes V1 minus V2. Now suppose if R1 is equal to R2 I have written, please change it to RF. If R1 is equal to RF, suppose this is also 1 kilo ohm and this is also 1 kilo ohm, the net value is 1. If it is 4 kilo ohm, this is 4 kilo ohm, net again 1. If it is 5 kilo ohm, this is 5 kilo ohm, both are 1. Now same 1 only. So now it is not R1 is equal to R2. If R1 is equal to RF, then V naught is equal to V1 minus V2. That means the voltage at the inverting terminal, non-inverting terminal is subtracted from the voltage at the inverting terminal, V1 minus V2. So you are going to get difference voltage. If suppose V1 is at 5 volt and V2 is at 2 volt, and what you are going to get? 3 volt. So that is the V naught subtraction you are going to get. Now the operational amplifier working as an subtractor circuit. I hope this you have understood. What you need to do is just go with the basics. First you need to draw this circuit diagram, try to write the equation. So this only we have achieved at the end. V naught is equal to RF divided by R1 into V1 minus V2. If RF and R1 both are same, then V naught is equal to V1 minus V2, which act as a subtractor circuit. So just go through the circuit, try to use the superposition theorem here, as we are using two independent voltage sources. Then use voltage divider formula. These are the two things which you need to do it. Then just use some arrangement. Finally you will arrive at this V naught is equal to V1 minus V2. I hope you have understood. If not, please comment. Thank you.